So we are talking about harmonic oscillators. And last time we did the case of an undamped oscillator. And so I did all the calculations for a system like this. But everything that we calculated works at any orientation. So this could be a hanging mass oscillating on a spring. All that matters are the spring constant and the mass, okay? So the frequency or whatever, the plot, if you plotted this over time, it would look exactly the same, no matter what the orientation is. Okay. And what we got for this was, if it's released from rest, you know, like an equilibrium position, at x equals L, what we got for this function is x as a function of time is equal to L times the cosine of the square root of k over m times t. Okay, so what this looks like is this is the undamped case. Okay, so we get something like that. Okay. And all of these graphs I'm going to show you, I mean, get oriented on it. I mean, this is just x versus time. All of the graphs I'm going to show you have the same value of m and the same value of k. Okay. So this is the first one, and you know, since there's no damping, this just goes on forever. The amplitude never decreases. This graph, I showed it being released from an x value of 0.05. And so the amplitude keeps going at 0.05 forever. If I increased the mass on this, what do you think would happen to this graph? Yeah.
The period will get smaller.
If I increase the mass, the period will get bigger. Think of like a really flimsy spring trying to make a truck oscillate in a frictionless environment. It actually will do it, but it'll take forever, you know, because that's a lot of mass for it to accelerate, you know. This is determined by how precisely that spring can accelerate the mass, sort of intuitively, you know. And so and if you increase the spring constant, increase the stiffness of the spring, you get the opposite. Then the period decreases, the frequency increases. Okay, so if the mass goes up, the frequency goes down, the period goes up. If you increase the k value, the frequency goes up and the period goes down. Okay, so that's the undamped case. Now we're going to do the damped case. And one thing I want to say about this before I go on, this is true of all of these. So in the horizontal case like this, it's pretty unambiguous what x equals 0 means. I mean, this thing's just sitting at rest. And it's sitting at rest where the spring is exerting 0 force, okay? But think about a mass hanging from a spring. Now there's kind of two things you might sort of think of as possibilities for x equals 0. One is when the spring is at its resting length. And then the other one is when the system is at equilibrium, where the mass is pulling the spring, stretching the spring out a little bit. Okay, can you picture what I'm talking about? So which one of those is going to be our x equals 0? So if gravity is parallel to the spring force, it doesn't have to be parallel. If it has like any, if any of the weight force is parallel to the spring force, you know, if any component of it is. X equals 0 means the hanging equilibrium position. Not the spring's undeformed position. So hopefully you can visualize what I'm talking about with that distinction. Okay, so now we're going on to the damp case. And most of this looks the same. We still have the cart with a mass m, and we still have a spring with a constant k. But now we have, in textbooks, they always call this a dash pot. I'm not sure what that comes from. Any of you car people, is that something that you've heard of in mechanics or anything?
What?
A dash pot.
Yeah. I'm calculus.
Okay, yeah, in calculus, yeah. I don't know. Well, anyways, it's a viscous friction. It provides viscous friction. So it's like what this sort of symbol is representing is that this is an enclosed container with oil or something inside, and there's a piston inside. And to move that piston, you have to fight the viscous forces of the oil inside. Okay. And the effect of that is that it provides a force that's proportional to the speed that this thing is moving. Okay, so a free body diagram in this case. We have the weight force, mg, a normal force. These two things aren't really going to matter. And then we have the friction force that, again, I'm representing like this. Friction, no, the spring force. And then we have the damping force, like a viscous friction force, that the direction works the same way. This is equal to c times x dot. So if so what that says is if x dot, this thing's moving in the positive x direction, that force is negative, it's fighting that motion. And if this is moving in the negative direction, then this is positive, and the friction force is opposite that. Okay, it's always fighting against the motion, fighting against the velocity. Newton's second law says 0 negative mg plus 0n plus negative kx 0 plus negative cx dot 0 is equal to the mass times the acceleration, and the acceleration is just horizontal. And that acceleration is x double dot. So I can take the x equation and rewrite this as negative kx minus cx dot is equal to mx double dot. And now rearrange this, and you get, and I'm going to divide everything by m again, so I have a 1 coefficient on the leading term. We got x double dot plus c over m x dot plus k over m x. Okay. This is a second order differential equation with constant coefficients. And remember what we did at this step last time? We had a differential equation that had the x double dot term and the k over m times x term. It didn't have that middle term with the first derivative. And so it was set up for us to immediately jump to assuming that this was going to have a sinusoidal solution. Mm-hmm. But that sinusoidal solution doesn't work here because of that first order term. Okay, so we got to try something else. And the thing that's going to work is, so we're going to assume a solution of the form x is equal to e to some constant times t. Okay. And now that we're assuming this form, obviously this this lambda, we're going to have to calculate that. You know, this isn't a solution yet. That's just kind of a placeholder. But now that we have this form, we can say, well, if it's this form, we do know that x dot is going to be lambda times e to the lambda t, and x double dot is going to be lambda squared e to the lambda t. Okay. And so let's plug these into the equation and see what we have. Okay. So we're going to plug this assumed solution into the governing ODE. And this is the governing ODE for damped oscillation. Okay, so we're going to plug it into this equation. X double dot, that's lambda squared e to the lambda t. Then we have plus c over m times x dot is lambda e to the lambda t. So c over m times lambda times e to the lambda t. And then plus k over m times what we're assuming for x. So that's k over m times e to the lambda t. And that's equal to 0. And now we can divide both sides by e to the lambda t. And we just get this quadratic formula for, this quadratic equation for lambda. So we got lambda squared plus c over m lambda plus k over m is equal to 0. Okay? What we're trying to find is lambda, so we can just use the quadratic equation for this. And so lambda So we're going to use quadratic equation to find lambda. And we get that lambda is equal to, C over M divided by 2 times A. A is 1. Plus or minus the square root of B squared minus 4 times 1 times K over M. So this is minus 4K over M, square root of all this, divided by 2A, so that's just 2 here. Okay, and now we can simplify this. Lambda is equal to, I thought you were coming up here to like whisper in my ear, like, you're in your underwear. So C over 2M plus or minus. Okay, so now with a little bit of algebra fiddling, you can simplify this. Notice that the C squared over M squared, you can, if we have everything over M squared, we can pull that out of the square root as just M. And so I'm going to think of this 4K over M as 4MK over M squared. And then we can pull that out. And so we get this second term that's equal to C squared minus 4 KM square root all over 2M. Okay, so that's our solution for lambda. And this is going to look qualitatively, fundamentally different depending on the nature of that square root term. If C squared is bigger than 4km, then this is a pretty straightforward thing, right? We have a real square root, and you just have the 2 roots, and then we put that into the solution. If C squared is equal to 4km, then we have repeated roots, real roots, still no imaginary stuff. And we have to format the general solution a little bit different. We'll get to that, but it's pretty straightforward. But things get more complicated, and where the sort of cool mathematical thing comes in is when 4km is greater than C squared. Okay, then that square root becomes imaginary. Okay, I mean, it's a negative square root, so we have an imaginary term. And that's when we'll see the relationship between imaginary exponentials and trigonometric functions. Okay? How many people have seen that in a class before? 1, 2. Okay. How many are just like, I'm not putting my hand up at 9:20 in the morning? That's okay. So, all right. So there's 3 cases. The first one is C squared is greater than 4km. Okay, this has 2 real roots. Think physically about this. What does this say about the damping? Well, we're saying C squared is bigger than 4km, so you can think of this as a case where we have a lot of damping. Okay? Right, relative to those 2 other things. And so this is going to be called the overdamped case. The second case we're going to treat is when c squared is equal to 4km. This is repeated real roots. And this clearly is some kind of border between two worlds of damping. You know, it's in between where that square root is positive and where that square root is negative, square root of a negative number. And so we're going to call this critically damped. This actually has a really important physical meaning. This instant right here, I mean, it's not an instant, this, when you have this exact relationship between the damping, the spring constant, and the mass, this is where you're returning to equilibrium the fastest. Okay, so this is called critically damped. And in the case of control systems, this is usually what you're trying to achieve. Okay? And then the last one, the cool one. It's actually sort of when you see the solution, you're like, all that work for this? But mathematically, it's the cool one. This is the case where 4km is greater than c squared. This is a case where you don't have much damping, and we're going to call this underdamped. Okay, in these two, you're not going to see oscillations. In this one, you're going to see oscillations with a decreasing magnitude. You know, like the magnitude keeps decreasing. Okay, so let's start with the overdamped case. So let's call, so if you look back at the roots, let's call that, this should be I left off the negative, like a stupid idiot. Okay, change that in your notes. Remember the quadratic formula? I guess I don't. Okay, overdamped case. Lambda is equal to, we're going to call it this first term, the negative c over 2m. I'm going to call that negative a. And then I'm going to call the square root over 2m term b. Okay? You with me on that? And so the solution is going to be that x as a function of time. Okay, so negative a is equal to negative c over 2m. B is equal to square root of c squared minus 4km over 2m. So we can plug that in at the end. But I'm just going to carry it around as a negative a and a b just to keep the math cleaner looking. So this is equal to some constant times the solution form using the first root. So this is C1 times E to the negative A plus B times T power. Just plugging those roots back into the solution form. Plus C2 E to the negative A minus B times T power. Okay, so this is the general solution in the overdamped case. And now we can use boundary conditions to put numbers on these things. And so on all of these, I'm going to make the same assumptions that I did when we didn't have any damping. I'm going to assume that we hold it in a position x equals L, and then we release it from rest. So we're going to assume that x at time 0 is L, and x dot at time 0 is 0. Okay, those are our two boundary conditions. We have the form of x. From that, we can take the derivatives, and we know that our x dot has the form c1 times negative a plus b times e to the power of negative a plus b times t. Plus c2 times negative a minus b times e to the power of negative a minus b times t. Okay, so I'll do the derivative condition first. Is that the easiest way? Well, let's do the just the x of 0 is equal to L thing first. So I'll use that as the first boundary condition. When you plug 0 in for time, the e to the powers become 1. Okay, not with each other, but they each become 1 individually. It's not like a romantic thing. I'm trying to say it's like, so we have, so what does this become? Just C1 plus C2 is equal to L. C1 times e to the 0 plus C2 times e to the 0 is equal to L. So C1 plus C2 is equal to L. I'm just going to do the second one, and then we'll solve these as a system. So the second boundary condition says x dot at 0 is equal to 0. Again, so using that x dot equation, we have that C1 times the quantity negative a plus b times e to the 0 power plus C2 times negative a minus b times e to the 0 is equal to 0. And so this says C1 times, so I'm going to multiply these out. The e to the 0s become 1 again. So negative C1a plus C1b minus C2a minus C2b is equal to 0. I guess here I'll say, from this one I'll go C2 is equal to L minus C1. And so I'll combine these two equations. And I get negative C1a plus C1b minus LA plus, okay, I'm trying to be too quick here. So minus, our C2 is L minus C1. And we're multiplying that by A. And then our last term is minus L minus C1 times B. And all this is equal to 0. So again, I'll multiply that out. Negative C1A plus C1B minus LA plus C1A minus LB plus C1B is equal to 0. And we get a cancellation here. And these two combine. So we have C1A. Yeah.
Would you cancel the LA? Shouldn't be C.
I did. Thank you. That would have taken me forever to find. Okay, so C1. So 2C1B is equal to L times A plus B. And so C1 is equal to L times A plus B all over 2B. Okay, so C2, then we can use this relationship here is equal to L minus C1. So I'm going to write this as 2BL over 2B. And then minus C1, so minus LA minus, right, it is BL. Okay? And we get that C2 is equal to L times B minus A over 2B. Okay. Okay, and what you get for this is, so now our total solution, I guess let's write that out, is equal to L times B plus A over 2B times E to the negative A plus B times T plus L times B minus A over 2B times E to the power of negative A minus B times T. Okay, so that's our solution. A and B, remember, those are just things we replaced earlier. That's these two things. Okay, so now if you replace those in the equation, it's kind of a messy equation, but that's all right. Okay, so what does this look like? Well, overdamped. It's called overdamped because it's too much damping to be ideal. Like, it definitely kills the oscillations fast. It kills the oscillations faster than anything else, but it also takes a long time for it to return to equilibrium because the damping is so strong, it keeps the spring from putting itself back in its natural position, Mm-hmm. So here is what that looks like. So overdamped. Okay. You can kind of see, you could see it if I zoomed in here, that it does have a slope that's equal to 0 at the start. Okay, so that's required by our boundary conditions. But it starts to die off very quickly, and you'll see it if you look at 1.5 seconds. It's still pretty far from its equilibrium position. Its equilibrium position is 0. Okay, so there's still a noticeable distance between the location of the mass at 1.5 seconds and the spring's resting position or the equilibrium position. Okay. Okay, so this is overdamped. And this is slow to return to equilibrium. Yeah.
So what's because obviously you have a force applied in order to make it go to, what function, or I guess it would just be it's bringing and pulling it back?
Yeah, the spring is pushing or pulling it back into equilibrium, but
It would be like you pulled it all the way and you just let it go.
Yeah, and it's just fighting that, rusty floor or whatever, I mean, so it's hard for the spring to push it back to equilibrium, but it does. The reason it does is, that's kind of a bad analogy, because if you think about dry friction, you get damping that's, you get friction that's so high that the thing just can't move at all, right? But if all you have is this viscous damping, remember that it's only proportional to the velocity. So the slower this thing is moving, the less damping there is. And so at some point, it's moving slowly enough that the spring can make progress. But it can't make fast progress because every time it tries to speed the thing up, the damping slows it back down, So that's the way this works. There's no viscous damping that would allow 0 progress of this thing back to equilibrium, but it would just take longer and longer the more damping you had. And like I said before, remember that all of these graphs I'm showing you are for the same mass and the same K value. This just has a damping value that's in the range that makes it overdamped. Okay, because remember what determines the type of damping you have is the relationship between C and that K and M. Okay. Any other questions about that one? That's the overdamped case. Yeah, you're normally trying to avoid that one.
So C is the viscosity of the fluid?
Yes. It's related to the viscosity, yeah. That's right. Oh my God. Look at how much time's gone by. Okay, so now we're going to go to critically damped. Yes?
For my homework, are we going to be using these equations or deriving from them?
I don't remember if I even have any problems on damped. Really, I just wanted to go through this because I like to hear myself talk. But I think, really, this is just something you're going to see in the future. And I think it's cool. And anybody who hasn't seen the connection between complex exponentials and sine and cosine is going to think this is amazing, And you've probably already wondered about it, even if you haven't seen it in a class, And my dad once was like, actually not once, over and over again, he would use imaginary numbers as the ultimate pointy-headed thing, just there's no purpose to it. Why are people doing math on imaginary numbers? And so one time, I guess when I was older, I was like, oh, you really can't do any electrical engineering or control systems without imaginary numbers. And he got all mad.
Yeah.
Okay, so critically damped. We'll see how far we get. Okay, so critically damped. So critically damped means C squared is equal to 4 km. And so that means that that whole square root term goes away. You know, this whole term of C squared minus 4 km square root over 2m, that's equal to 0. And so our roots are lambda and lambda, you know, two repeated real roots. So I'm going to make I'm going to call it negative a again, because this is always negative. Negative a is equal to negative c over 2m. And so what do you do in a differential equation like this when you have the two roots, like when you have the two repeated roots? Notice that in the overdamped case, we had the two different roots, and we set it up as some unknown constant times e to one of those roots times t, plus another constant times e to the other root times t. Well, now we can't do that because that just becomes a single constant times e to the one root times time. And obviously we're losing information there. Well, the trick that you use there, so for repeated roots, we're going to assume a general solution that's equal to, so x as a function of time is equal to c1 times e to the negative at. Okay. And then the one where we would use the other root, but we don't have another root, we're going to do this as c2 times t times e to the negative at. Okay. I'm not going to prove why that works, but that's the form that works in this case. Okay, so this is the general solution to the critically damped case. And now we have to go through the boundary conditions. So again, our boundary conditions are that at time equals 0, x is equal to L, and at time equals 0, x dot is equal to 0. X dot from that general solution is C1, negative C1a e to the negative at, plus, notice you have to use the product rule here, plus C2 e to the negative at minus C2a times t times e to the negative at. Okay? Well, let's first use this boundary condition. If you plug in 0 for t, you get that x at time 0 is equal to C1 times e to the 0 plus, well, this time, I almost fell for this trap, but look over here, when t is equal to 0, that second term goes away, okay? And so this is equal to L, so C1 is equal to L. And then I'll update this function. So we have x as a function of time equal to L e to the negative at. And then we have plus C2 t e to the negative at. And then x dot updated is negative L a e to the negative a t plus C2 e to the negative at minus C2 a e to the negative at. And now I'll use the other boundary condition that says x dot at 0 is equal to 0. This all is x dot. I forgot the t here. Change the order. Okay, so plug in t equals 0, and you get negative LA times e to the 0 plus C2 times e to the 0 plus 0 is equal to 0. And so C2 is equal to LA. Okay, and so the final solution is x is equal to L e to the negative at plus L a t e to the negative at. And I want to show these two next to each other because by just looking at one, you can't see too much, but so I'm going to put down the overdamped case. And then over here, I'm going to put down the critically damped case. These are the same M and the same K. So this is overdamped. This is a slow return. To equilibrium. This is the critically damped case. And this is the fastest return to equilibrium. Bless you. And you can see it there. I mean, look at, I said before, look at 1.5 seconds, but you can look at 1 second or 1.5 seconds or anywhere in there. The critically damped case is already almost indistinguishable from 0, while this one is still noticeably far from it. Okay? So those are the two that critically damped is the most important of these three solutions. Underdamped is the most mathematically interesting of the three solutions. Overdamped is nothing. So next time we'll do underdamped, and we'll see how, in this case, like you can't tell, there's no visible oscillation at all, right? It's just a curve returning to equilibrium. In the underdamped case, you're gonna see a very clear sinusoidal shape to this thing. Okay, that's all.